30 years ago, we detected the first planet outside the solar system, orbiting a distant star.
Since then, we've found thousands of these so-called exoplanets, alien worlds beyond our solar system. And we're finding out more and more about them.
This month we're in Edinburgh to see the latest technology that will give us a better picture of these distant worlds.
We'll be talking to the people who are not only detecting these planets, but are also trying to understand their atmospheres.
And as well as exoplanets, we'll be joining the hunt for an even more elusive target, an exo-moon.
And Pete will be searching for the most distant planet in our solar system, Neptune.
Welcome to the sky at night.
In the last couple of decades, we've discovered thousands of planets outside our solar system. Whilst we've always dreamed of finding Earth-like planets, what we've actually found is a fascinating variety of worlds quite unlike our own. When we started looking for exoplanets, we thought we'd find worlds like the ones in our solar system. But reality turned out to be rather more complicated than that. When you find an exoplanet, there are two things you should care about. The first is the size. So we're going to put big planets up here and small planets down at the bottom of the graph here. The other factor that matters is how much starlight your planet receives. That determines its temperature and the environment in which it lives. So we'll put hot planets down in the bottom left, and we'll put cold planets over on the right-hand side. Now, the first exoplanet was found in 1989, so we'll put that one up. And then by 1999, we'd already found a whole host of worlds, and we could see that things were going to be rather different. These planets up here are hot Jupiters. They're large, like Jupiter or Saturn, but they're much closer to their stars than Mercury is to the Sun. So these are unusual planets, the kind that we don't have in our solar system. Now, 10 years on, we've really begun to fill in the smaller planets. We've got plenty of Neptune-sized worlds and plenty of Earth-sized worlds down here. In fact, the most common size of planet are these green ones on the graph, these Neptune-sized planets. In fact, there's an awful lot of planets that are smaller than Neptune, but bigger than the Earth, what are called super-Earth planets. That's a common type of planet that we turn out not to have in our solar system. Now, we can label this diagram according to the types of planets. So we've got the cold gas giants. We've talked about the hot Jupiters in the top left here. The ice giants in between, Uranus and Neptune in our solar system, but here much closer to their stars than those distant worlds are round here. In the bottom left, my favourite kind of planet. These were completely unexpected. The lava worlds, Earth-sized worlds that are so close to their stars that the temperature on their surface would be high enough to melt rock. So you certainly couldn't stand there. And we don't know how these worlds formed. They can't have formed in situ. Maybe they were the hot Jupiters of the past. They've had their atmosphere boiled away by spending too much time close to their star. The part of the diagram that gets most attention is down here in the bottom right. If we zoom in, we can put up some crosshairs for Earth. So we would lie smack in the middle here. And we're beginning to find planets that are pretty close to being Earth-like. They get the same amount of light and they're the same size. There's Proxima Centauri's planet, our nearest exoplanet, TRAPPIST-1e in the multi-planet system that people get very excited about. And then a new discovery, Teegarden B, almost the most Earth-like planet we know, a planet around Teegarden's star, a small red dwarf just 12 light years away. So we are finding that around our nearest stars we can detect properly Earth-like planets. The discovery of exoplanets is a great adventure story. 30 years ago, the only planets we knew of were those within our own solar system. But now we know that planets are common and peppered throughout the galaxy. But how were these astonishing discoveries made? To find out, Maggie went to meet exoplanet expert David Armstrong at the University of Warwick.
Hi, David.
Hi.
Thanks for taking the time to meet up with us. So we're talking about exoplanets, but can you tell me, they're quite hard to detect. So how were the first ones found?
Well, the first ones were found via something called the radial velocity method, or the wobble method.
Yes.
So this is when a planet orbits the star. The star moves just a little bit as the planet orbits.
Oh, yes.
So if we take the light from a star, we can split it out into lots of different colours or wavelengths.
Oh, yeah, a spectrum.
Yes, spectrum. So in a spectrum like that, you'll see these black lines, for example, are sort of the specific signature of a star.
Okay, so that's the spectrum of the star, and those are absorption bands, so chemicals absorbing the light.
Chemicals and molecules in the star's atmosphere. So as the star moves, we see them move just a little bit backward and forward. Oh, right. Much like sound does as you hear an ambulance coming towards you in a way.
Oh, the Doppler effect.
Yeah.
Yes.
As a planet orbits, its gravity pulls on its star, making the star move or wobble. By looking for Doppler shifts, we can detect these tiny movements, the telltale sign that there's an exoplanet in orbit around the star.
So, as you see, when the star's moving towards us, the lines go just a bit towards the blue end of the spectrum, and then as it's moving away, you go a bit towards the red end.
Okay.
And we can use that to work out just how fast the star's moving, down to a level of even a few meters per second, like a brisk walking pace.
Whoa. So this is a star moving that small amount, and we can detect it using this method?
Yes.
Are there examples of exoplanets that were detected with this method?
Yeah, so one great example is Proximus NB, which is a planet orbiting the star nearest to the Sun.
Oh, yeah, our next door neighbour star.
So it's only 4 light years away from the Earth. And there's a terrestrial planet, really. It's actually colder than the Earth, this planet. But not too cold, it's in the habitable zone.
Okay, yes.
There's some fascinating projects around to try and send a CubeSat there, for example.
And this was detected using this method?
Yes.
Then what did we go on to? Were other methods employed?
Yep, so the way we've found most planets that we know of today is something called the transit method. If a planet passes between us and the star that it's orbiting, it'll block out just a little bit of the light from that star. And if we're measuring the brightness of the star over time, we see this characteristic dip. So most of the planets we know are found that way. There's over 2,000 of them through the transit method now. A nice example would be TRAPPIST-1, the TRAPPIST-1 system. The TRAPPIST-1 has 7 planets, and 3 of them are within the range where we expect liquid water might be possible on the surface, depending on the atmosphere of the planet, which we don't know yet.
Oh, yes. Well, that's quite a find.
Yeah, no, it's a fantastic discovery.
So when we look at there, the stars that we see, most of them have planets going around them.
Yes. Yeah, no, it's fascinating, really. And, 20 years ago, we had no idea of any of this.
Yes. And I think it really sets our place in the universe. For a while, we thought we were the only solar system, but now they seem quite commonplace.
Yes, indeed.
Most of the exoplanets we've found so far were discovered by a space telescope called Kepler. It found over 2,500 of them before its mission ended in 2018. But now there's a new planet-hunting telescope called TESS that could tell us so much more.
Kepler found these thousands of planets, but the trouble with most of them is that they're orbiting stars too faint for us to do anything else with. Look at the planet's atmosphere, for example. So TESS, by observing the whole sky, we see many more brighter stars. And then hopefully that will lead to planets orbiting those brighter stars, and then we can start to do many other studies.
You work on TESS data. What sort of things are you hoping to find?
So what I'm looking for is to use the radial velocity method to measure the masses of planets discovered by TESS. So that lets us look at some of their composition and their density. What we're really looking for is very hot planets where the outer atmosphere or envelope might have been evaporated. So this is one way that we might be able to expose the core of a planet and measure it directly and then study the interiors of planets. It's very hard to do in any other way.
Yes. TESS has only been up and running for a year. How long will it run?
So the baseline mission was for 2 years, 1 year on the southern hemisphere, 1 year on the north, but it's already been approved for an extension. And the spacecraft itself can carry on for much longer than that, so perhaps many more.
It's a really exciting time, I think, for exoplanets, and it's fantastic to hear about the work you're doing, and we're looking forward to coming back again and hearing more.
Thanks.
Thanks very much.
One of the most exciting things about TESS's search for exoplanets is that everyone can take part. Finding planets is just a matter of looking for patterns in data, something humans are surprisingly good at. One of the projects that I work on asks volunteers to help find planets by looking through the vast amount of data coming back from TESS. We've just put new data up on the site, so go to planethunters.org and see what you can find. So far, we've found thousands of planets in enormous and wonderful variety. Although we've learnt a great deal, all I want to be able to do is see an exoplanet. And here in Edinburgh, they're building an instrument that should allow us to do just that. This is the UK Astronomy Technology Centre in Edinburgh, and engineers here have designed and built a truly remarkable camera. After more than 2 years of hard work, the camera, called 𝑆𝑝𝑎𝑐𝑒, is now at the testing stage. The camera needs to be sensitive enough to capture the faint infrared light emitted by exoplanets. And there's another problem. What light exoplanets do give out can get swamped by the light from their vastly brighter host stars. I went to meet Martin Black to find out how the camera overcomes these challenges. Hey Martin.
Hi.
How are you? I'm going to interrupt. What on earth are you playing with here?
So what I'm working on here is a camera for an instrument called 𝑆𝑝𝑎𝑐𝑒 that's going to help us look for exoplanets.
What are the challenges that brings?
The biggest one's probably we've had to build a camera that works in the infrared, but what it means is what the camera you build has to be cooled to very low temperatures. So what we've got here is the actual instrument itself on top, and then everything underneath is just there to keep it cold, keep it at very low temperature.
And so those pumps that we can hear, that's the cooling system?
Yeah, that's correct.
So what's the hardest thing about trying to take a picture of an exoplanet?
So when trying to take a picture of an exoplanet, the star that it's orbiting is a lot brighter, hugely brighter than the planet itself. So you have to try and get rid of that light. And the way we're doing that in 𝑆𝑝𝑎𝑐𝑒 is using what's called a vortex coronagraph.
Great name for anything.
It is a really good name. Now this is essentially a diamond which has a very small structure etched into its surface, and this lets us null the starlight. Now the thing to keep in mind with this is the starlight is in the middle of what you're looking at.
You point the telescope at the star,
yeah,
right?
But the planet is just off to the side. That light is coming in at a very, very small angle, which is tiny, but it's enough for us to distinguish. And what we can then do is cancel out the starlight in the same way like a pair of noise cancelling headphones work.
So this is a complicated piece of kit. How do you test to make sure that it's working before you ship it off to the telescope?
So the stage we're at just now is we've finished building it all and we've sort of done the initial testing to make sure everything works in the cold environment. A lot of things jam up when you go cold. We then start putting light through the instrument. So what I've got here is essentially a small, very small artificial star, which we can then look to see how good that star looks, check the quality of it, and move that around so that we know that our entire field of view is in focus and working the way we want it to.
How's it going?
It's going pretty well so far. We've got 2 of our 3 cameras tested and they're working well. So we've now got starting our major test campaign to go through all the different modes we have to check.
What will happen once you're done with your testing?
So once we finish our testing here, we package this up and we send it to Germany. There's other parts coming from all across Europe that will all arrive in the lab in Germany. This gets bolted onto the rest of the instrument.
And where will the whole lot be installed? Which telescopes is this going?
So this is going to the VLT in Chile, the Very Large Telescope, onto UT4, which is the special one that's just had its adaptive optics upgrade, which is a unique thing in the world, and that's why we're going to go and take advantage of that.
Well, look, I won't get in your way any further. I'm really looking forward to getting data from this instrument, so good luck, and we'll come back and talk to you on the next project.
Thanks very much.
Thanks. It's astounding to think that we can actually image planets around another star. But as yet, we've only managed to do this for a handful of exoplanets. The camera that Martin and the team are building will change all of that, helping us see more planets in more detail than ever before. Taking pictures and actually seeing exoplanets is wonderful in itself. But perhaps more fascinating is what we can learn from these images. I talked to Beth Biller from the University of Edinburgh, who uses direct imaging to try and understand exoplanet atmospheres. So we now know of thousands of exoplanets, but most of them we've never seen. We only detect them indirectly. You're doing something much more exciting. We get to see your planets.
Yes.
What do you work on?
So I work on a method where we actually try to take pictures of planets around stars. So it's kind of like trying to image a firefly next to a lighthouse. if your Firefly and Lighthouse are in Dublin and we're here in Edinburgh.
When you do that, this sort of direct imaging, the results are spectacular. What are we looking at here?
So this is the HR 8799 system. The star, it's about 2 times the mass of our own star, represented by this little star here. And so you can actually see the motions of the planets around the star.
And there are, what, 1, 2, 3, is that a 4th one there?
That's a 4th one there.
And it's a remarkable image. There's something special about watching planets orbit a star. We've seen it millions of times before, but not in reality.
Yes.
But what can we find out about the planets in the system?
The advantage of direct imaging is that we have light directly from the atmosphere of the planet itself. And once we have light from the atmosphere of the planets, we can actually disperse the light into its component wavelengths and look at spectra.
And so we can show that. We've got a demo
Yes.
here. Let me get the computer out of the way. Let's do that. So
Right.
what are these things?
So this is an argon lamp. Let me switch it on, and it is a lovely purple color.
Okay.
So this is just heating up argon gas and seeing at what wavelengths it emits. This
What
is
is this?
helium.
Oh, it's a nice colour. Okay, and what happens with the
So this is our
diffraction grating?
diffraction grating, and it will break the light into its constituent wavelengths. So if we
Okay.
bring it up,
Oh, look at that.
you can see 5 or so distinct spectral lines here, and combining all of those together gives us this characteristic kind of peachy color.
And so if we saw features at that wavelength in the atmosphere of a planet, we'd know there was helium there.
Exactly, yeah.
And what about argon? What do we see here?
So this, you already can see there's much more at one specific wavelength, there's fewer lines.
And so the principle is if you look at the light, you can see these lines at particular wavelengths, we can find out what the atmosphere is made of.
Exactly.
Can we use these techniques to look for life?
Not in these planets. These are highly uninhabitable planets. Below the hot silicate level, you expect the clouds to possibly be molten iron droplets.
Okay, that sounds
But-
exciting, but not very friendly. So.
No, it's not a great holiday spot. All these techniques we're using now for these very warm planets, we're hoping to extend to cooler, potentially habitable planets, especially rocky habitable planets.
How hard will it be to find planets that we can go after the atmospheres like this, the habitable planets, I mean?
Yes. So to do this via direct imaging is still going to be a couple of decades off because you need incredibly good contrast. It's something we're going to be doing probably in the 2030s with giant space telescopes.
Now, this is fascinating work and we want to do more of it, which means new instruments, new telescopes. We've just seen the camera that's being built down the road. How will that instrument, 𝐴𝑠𝑠, help you with this research?
So one thing that's particularly exciting about 𝐴𝑠𝑠 is that it will push to longer wavelengths that are hard to access from the ground. Now the problem with these wavelengths is that everything is glowing. The air is glowing, your telescope is glowing, your instrument is glowing. And so we haven't studied the spectrum of these planets at these wavelengths very much, but there's a lot to find there.
Well, it's exciting stuff. As soon as you get on Sky, we'll come back and find out what you're seeing. Thank you very much. It's amazing to think that we can tell so much from pictures of what is nothing more than a point of light. And it's going to be fascinating to find out what the next generation of cameras brings us. Imaging exoplanets is beyond the scope of the amateur astronomer. But there are other hard-to-find planets out there, and Pete went in search of one. Neptune.
Neptune is the outermost of our solar system's 8 main planets. It is 30 times further from the Sun than the Earth and orbits slowly. It takes 165 Earth years to go around the Sun and has completed only 1 full orbit since discovery. And in just a few days' time, Neptune will be at opposition.
So let me show you what I mean by the term opposition. Now this isn't to scale, but this light represents the Sun, this light represents the planet Neptune, and this sphere represents the Earth. Now the Earth is in orbit around the Sun, like so, and when it's in this position here, Neptune is in the sky fairly close to where the Sun is. But as the Earth moves round, so it's in a position like that, there's a line between the Sun, the Earth and Neptune. So Neptune appears in the opposite part of the sky to the Sun, and that's what opposition.
Over the course of September, appearing to move just a small distance from the star by the end of the month.
Now, to get you the best possible view of Neptune tonight, I brought my largest telescope out. It's a 14-inch telescope with great light gathering properties, and it can also see really fine detail. But to be honest, you can see Neptune even with a small telescope.
The camera mounted on the telescope was linked up to my computer, so I could see what it was picking up. But thanks to the clouds and hazy atmosphere, I was struggling to find Neptune. Persistence, however, eventually paid off.
Well, I've got it. I've got Neptune. And what I can see is that the planet has a disk. It's a very tiny disk. And I can pick out the colour as well. And I can see that it's got a definite bluish hue to it, which is rather pretty.
The blue colour is the result of Neptune's methane-rich atmosphere. And if we look very closely, it's possible to see more than just the planet itself.
Okay, so I've upped the sensitivity of the camera, and what I can clearly see now is Neptune's largest moon, Triton. It stands out really well in amateur equipment, and it's pretty amazing to think that you're looking at a moon going around the most distant main planet in the solar system.
Voyager 2 flew past Triton in 1989, giving us these amazing images. It's a strange, geologically active world, scarred by rising blobs of ice, faults and volcanic pits.
Moons are incredibly varied and interesting worlds. We find volcanoes on them, enormous water geysers, and methane lakes. And our solar system is full of them. So, if we're finding exoplanets, should we also be finding exomoons? I called exomoon hunter David Kipping to find out the latest on the hunt.
So, David, why is it important to detect exomoons?
There's three important reasons. The first is that we look for life on exoplanets, but who's to say that life can only reside on planets? Why not moons as well? Second reason is that the moon seems to have had a large influence on the history of our own Earth. The Earth spins around this axis, and that axis is tilted by 23 degrees. Now, if we didn't have the moon there, we took the moon away, that axis would sort of wander around over millions of years, and that would cause a much more chaotic climate for our planet. It might be difficult to do agriculture, for instance, if you had a climate like that. So having a large moon seems to have been beneficial to complex life on this planet. And then the third reason is just to really understand and complete the story of how planets and moons and planetary systems as a whole form and evolve through time.
Now, detecting exoplanets is pretty challenging stuff, but detecting an exomoon must be harder. So how do you go about detecting an exomoon?
That's right, it's certainly harder, and probably the simplest reason why it's harder is just because these things are expected to be rather small. The way we actually make the detection is very analogous to the way we look for exoplanets. First off, if a planet transits in front of a star, causes that dip in light, then we should expect that if there are moons around that planet, then they will also cause a dip in starlight. And we can look for those. And on top of that, the moon has its own mass and therefore its own gravity, and that gravity causes the planet to sort of wobble about as it goes around on its orbit. The moon does this for the Earth. So for instance, if you're an alien observing the Earth transit in front of the sun, sometimes the Earth would seem to transit the sun 5 minutes earlier than you would expect it to, and other years you look at it, it would happen 5 minutes later. And that 5-minute deviation is completely due to the moon.
So 5 minutes seems like a detectable amount. So do we have the technology to do this today?
We certainly can detect exomoons if they were large enough, and that's really the open question. We don't know how big exomoons get. My bet is that there are large moons out there, and thus we should be able to find them, and that's what we're trying to do.
A little while ago in the newspapers it was reported that the first exomoon had been detected. Now, you were involved in that story, but that's not quite true. So what happened?
Yeah, sometimes things do get slightly exaggerated in the reportings. It is true that we found something though. So we were observing a giant planet, similar size to Jupiter, move around its star, and we actually think we saw some little wiggles just before and after the transit, which are that telltale sign of an exomoon. So we asked Hubble if we could observe that star, and we got the observations, we looked at it, and indeed we do see something very interesting. We see another big dip that corresponds to a Neptune-sized moon orbiting a Jupiter-sized planet. So that's very surprising in a way. I mean, nobody really anticipated a Neptune-sized moon around a Jupiter-sized planet. We would like to point Hubble at it again, see it happen another time, and then I would feel much more comfortable calling it a slam dunk detection.
So have you got plans to do that, to get Hubble to look at it again?
We certainly will try, maybe again for this system and for other systems like it in the future. The last transit that happened was actually in May of 2019, this year. And for that transit, we had a very clear prediction as to where the moon should be. Unfortunately, if we go another 300 days in the future and we look at the next transit after that, we don't have a good prediction. And that's just because whenever you predict further and further into the future, the predictions become ever more uncertain. And even if I see something, I can't point at it and say, hey, that's exactly where I predicted it should be. And so that's going to weaken our case when we go to Hubble and say, give us telescope time. So it's really a shame we didn't get that May transit.
Are you looking at other candidates, other exomoon systems?
We are. We're doing two searches at the moment. One is to look at planets which are very similar to this Kepler-1625 exomoon candidate already, so cold Jupiters on wide orbits around this. The second thing we're doing is actually using the methods of deep learning, artificial intelligence techniques, to try and look for the signatures of exomoons. Those are the two big surveys we're working on right now.
This is such fascinating stuff, and we're really looking forward to meeting up with you again and finding out about that first detection, first confirmed detection.
The extraordinary mission to Saturn next on BBC 4. NASA says it's goodbye to Cassini with Horizon.